At the end of this video, you should be able to list the total number of electrons needed to fully occupy each main energy level, and state the Aufbau Principle, the Pauli exclusion principle, and Hund's rule. Chapter 4, Section 3, Electron Configurations. The quantum model of the atom improves on the Bohr model because it describes the arrangements of electrons in atoms other than hydrogen. The arrangement of electrons in an atom is known as the atom's electron configuration. Because the atoms of different elements have different numbers of electrons, a distinct electron configuration exists for the atoms of each element. Like all systems in nature, electrons in atoms tend to assume arrangements that have the lowest possible energies. The lowest energy arrangement of the electrons for each element is called the element's ground state electron configuration. A few simple rules, combined with the quantum number relationship discussed last section, allow us to determine these ground state electron configurations.
The electron configuration of an element is the arrangement of electrons in an atom of that element. For example, the electron configuration of sodium is 1s2, 2s2, 2p6, 3s1. This orbital diagram shows you which orbitals are filled in the atom. For example, sodium has 2 electrons in the 1s orbital, 2 electrons in the 2s orbital, 2 electrons in each of the 2p orbitals, and 1 electron in the 3s orbital. The electrons can be represented by arrows pointing up or down. The sequence for writing an electron configuration usually follows the order shown in this diagram. Each s orbital can hold 2 electrons. Each group of 3 p orbitals can hold 6 electrons. Each group of 5 d orbitals can hold 10 electrons. And each group of 7 f orbitals can hold 14 electrons. By filling in the orbitals one at a time, electron configurations can be determined for most elements.
Rules governing electron configurations. To build up electron configurations from the ground state for any particular atom, first the energy levels of the orbitals are determined. Then electrons are added to the orbitals one by one according to 3 basic rules. Remember that real atoms are not built up by adding protons and electrons one at a time. The first rule shows the order in which electrons occupy orbitals. According to the Aufbau Principle, an electron occupies the lowest energy orbital that can receive it. Figure 4-16 on page 105 of your text, or on the screen now, shows the atomic orbitals in order of increasing energy. The orbital with the lowest energy is the 1s orbital. In a ground state hydrogen atom, the electron is in this orbital. The 2s orbital is the next highest in energy, and then the 2p orbitals. Beginning with the third main energy level, n is equal to 3, the energies of the sublevels in different main energy levels begin to overlap. Note in the figure, for example, that the 4s sublevel is lower in energy than the 3d sublevel. Therefore, the 4s orbital is filled before any electrons enter the 3d orbitals. Less energy is required for 2 electrons to pair up in the 4s orbital than for a single electron to occupy a 3d orbital.
The Aufbau principle states that an electron occupies the lowest available energy orbital. The Aufbau principle is used to describe the order of electrons in an electron configuration. For example, fluorine has 9 electrons. To find the electron configuration of fluorine, simply fill electrons into the orbitals in order of increasing energy. First, fill the 1s orbital, then the 2s orbital. That leaves 5 electrons. These will go in the 3 2p orbitals, which can hold up to 6 electrons. That means the electron configuration of fluorine is 1s2, 2s2, 2p5.
The second rule reflects the importance of the spin quantum number. According to the Pauli exclusion principle, no two electrons in the same atom can have the same set of 4 quantum numbers. The principle, angular momentum, and magnetic quantum numbers specify the energy, shape, and orientation of an orbital. The two values of the spin quantum number allow two electrons of opposite spins to occupy the orbital. See figure 4-17 on page 106 of your text or on the screen now.
The first 3 quantum numbers describe the energy, shape, and orientation of an orbital. For example, the first 3 quantum numbers might describe an electron in the 3d xy orbital. The Pauli exclusion principle states that no 2 electrons in the same atom can have the same set of quantum numbers. But each orbital holds 2 electrons. So how can we distinguish between these electrons? The spin quantum number distinguishes between 2 electrons in the same orbital. Each electron is labeled with a spin number of either +1/2 or -1/2. The 2 electrons in the 3dxy orbital have different spins.
The third rule requires placing as many unpaired electrons as possible in separate orbitals in the same sublevel. In this way, electron-electron repulsion is minimized so that the electron arrangements have the lowest energy possible. According to Hund's rule, orbitals of equal energy are each occupied by 1 electron before any orbital is occupied by a second electron. And all electrons in singly occupied orbitals must have the same spin. Applying this rule shows, for example, that 1 electron will enter each of the 3 p orbitals in a main energy level before a second electron enters any of them. This is illustrated in figure 4-18 on page 106 of your text or on the screen now. At this point, you should be able to list the total number of electrons needed to fully occupy each main energy level and state the Aufbau principle, the Pauli exclusion principle, and Hund's rule.